there's only one expert today, plus questions from the chat maybe. And we will try and move as fast as possible, but not too fast that people miss the details. So if that's okay.
You have, amongst your 25 conferences, have you had any on vaccines yet?
What did you ask, Steve?
Did you have any of your 25 master classes? Have there been any other ones on vaccines?
No, this is the first one on vaccines, and we're hoping to do one or two of them. We hope to do one with the Jenner Institute if they would be willing. But this is the first one, and it's going to be pretty comprehensive, actually. So we will talk a little bit about the entire vaccine portfolio, some RTSS work, and then spend about 60% of the time working, talking about Sanaria portfolio.
Sure.
Yeah. Okay, so I'm going to invite our colleague Bart Knowles. Bart and the Malaria World community have agreed to host this class also on their site after this. So they're going to pull it out as well. And Bart might have some additional questions as well. So I've just let Bart in advance. So as you can see, we already have 57 people waiting on the line. There'll probably be more people joining. So if that is okay with you, I will let everybody in. Is that fine?
Perfect.
Shayla, any specific notes? Ali?
We can start, Fred.
Okay. Hi, Bart. Good morning.
Hello from the Netherlands.
Hello. All right. So we admitting everybody now. Good morning, everybody. Please welcome to the 25th edition of the IFACARA Masterclasses. We ask everybody joining to kindly mute their microphones and their videos, except for our experts and co-hosts. Today, we have a fantastic session lined up with Professor Steve Hoffman, who is the Chief Executive Officer of Sanaria. Steve, I understand that Sanaria means good air. Is that right?
It actually means healthy air. So if
healthy air.
Malaria is bad air, Sanaria is healthy air.
Which is that an Asian word or Italian word as well?
Italian. It's an Italian word.
Italian as well. Healthy air. That's a good name. It's a wonderful name. Dear everybody, you will notice that we are live also on our YouTube channel at IFACARA Health Institute. The session today will be about malaria vaccine. We will talk about the development path for the vaccine candidates that we have today, including, of course, the work that has been done on the RTSS. This is the most advanced vaccine we have today. But a big portion of our discussion will focus on the sporozoid, the whole sporozoid vaccines that have been developed by, and are being developed by Sanaria. Our guest speaker today is Professor Steve Hoffman. We have done a review of his work and his colleagues and created a storyline that will guide our discussion today. You notice that we have a new co-host with us today, Dr. Ali Olotu. Ali Olotu is a clinical epidemiologist and a vaccine trialist, a drug trialist. He works with us at IFACARA Health Institute. He is also the head of the Interventions and Clinical Trials Department. And Ali's got long experience working on also the RTSS and is currently testing a vaccine candidate called RH5 together with our colleagues from England. So Ali, welcome as well.
Thank you very much, Pedros.
Right. We are still admitting new participants. We will be starting the class in approximately 1.5 minutes. And again, thanks to everybody for making time to join with us today. And appreciations in particular to people who have sent invitations to their colleagues. And if there are experts in the meeting who wish to contribute to the discussion, we can do this using the chat function. Please keep this active and let us know if there's anything that you might want to talk about as well. We may occasionally speak about a subject that is very close to your heart, or we may occasionally raise an issue that is associated with what you're working on. In cases such as that, if you would like to make any comment, please use the chat box. You can either send me a private message or Shayla or Ali, or we prefer that you just broadcast it to all. And then on that basis, we can carry on with the discussion. Ladies and gentlemen, we will start in approximately 30 seconds. Again, Steve, thank you so much for making time. I know that there are colleagues of yours from Sanaria joining with us. Yesterday, I've had a conversation brief by email with Dr. Billingsley, who hopefully is in the call as well. So welcome to the other Sanaria family members as well.
Well, Friedrich, thank you so much. And I just want to say at the outset that I'm really impressed by what you put together with these master classes. And it warms my heart to have as the hosts, you and Ali from IHI and Sheila from Chai, but in Nairobi, because the first place that I actually did any kind of malaria research in Africa was in Western Kenya, in Saradidi and Kisumu, which is the Kenya connection. And the first assessment of PFSPZ, Plasmodium falciparum sporozoites, by injection was, of course, done by the Ifakara Health Institute in Bagamoyo. And the first studies that we did in Central Africa and Equatorial Guinea were led by Ali. So we're all one family here trying to solve a pretty major problem or major problems. And it's really quite wonderful to be here. I see many people on the list that I know. I wish I could call you out all by name, but we have some very prominent malariologists, former head of the malaria branch of CDC, current head of the malaria branch of CDC, not to mention many, many others. So thank you.
Thank you very much. Thanks for raising these issues. We have a lot of stories to discuss today, from Saradidi, Ifakara, Bagamoyo, all the way. We will be talking about all that today. And actually, Steve, as we begin this, we have a very, very broad question for you, but a fairly important one. Steve, do you believe that we are on the right track to eventually bring malaria under control?
Wow, so that's a pretty broad question, and the answer, I think, is yes. And perhaps I can step back for a second and try to put malaria in contrast, or with other diseases. So we've all seen, I believe, the statements from WHO and the analysis that shows that in 2020, there were more deaths in Africa from malaria than there were from COVID-19, the pandemic that we're all experiencing. Tom Ritchie from our group has done a very crude type of analysis of DALYs, disability adjusted life years lost in 2020 from malaria versus COVID-19. And again, this is in the world. Our assessment is that malaria may have been responsible for perhaps 5 times as many DALYs lost as COVID-19. It doesn't, of course, COVID-19 is incredibly important, and it's killing older people as opposed to young children, and that's why the formula comes out with that type of result. But the impact of malaria is devastating. We did really well in the first 15 years of the 21st century. We're now investing $3 to $4 billion a year in malaria control efforts. But we've seen a plateauing, and this has been highlighted by Pedro Alonso from WHO, that in the last 4 or 5 years, there has been essentially no change in the number of cases or number of deaths from malaria, despite this incredible investment. And that's in part due to there's a lot more people, and particularly in Africa, than there were 20 years ago. So the incidence rate may be actually lower, but the problem is huge. And again, I'd like to do a quick comparison with COVID, right? So when we started COVID, and even now in certain countries, we frequently see something called the reproduction number, or R0, talked about. And can anybody, can this be interactive, or do I just talk? Can someone tell me what they think the COVID, what we've been told the COVID-19 or SARS-CoV-2 R0, a reproductive number, is? How many people, if one person gets it, how many people get it from that person?
You can type it on the chat box. Steve, a quick answer from me, just above 1.
Well, it could be 2. It's been said 1, 2, 3. My son, who was an internal medicine resident now and was then a medical student, wrote a paper, said that in New York it was up to 5. So the whole concept of R0 actually began to some extent with Ronald Ross, the discoverer that mosquitoes transmit malaria, but was really put into place by a fellow, by Professor McDonald, in the early 1950s. And it was about malaria. And what Professor McDonald said in his original papers was that the R0, the reproduction number for Anopheles culisafaces, which was the primary vector in India, was about 5. And in India in the 1950s and 60s, with the World Malaria Eradication Campaign, they brought the number of cases down to about 50,000 cases from nearly 100 million, I believe, in the country, because the R0 was quite low. In sub-Saharan Africa, and there are many different estimates of this, but McDonald estimated that for Anopheles gambiae, the R0, or reproduction number, could be as high as 3,000.
Wow.
So it gives you an idea of the transmissibility and the problem that we face in terms of the question that you ask, which is, are we on the right track? Of course, we're on a right track, but this is not an easy disease to deal with.
Right.
And, we are throwing whatever we can at it. But as has been stated, I think a number of times by WHO, the Global Malaria Program, we need new tools. And
right.
Of course, we're here today because the most effective tool against any infectious disease is a vaccine or vaccine.
So Steve, you talked a lot about, I would like us to just very briefly talk a little more about the epidemiology of malaria in Africa compared to the rest of the world. So the R0 in Africa, you say, could be as high as 3,000, given the early estimates. Of course, now it's much lower with the RCs. Many times people compare what has happened in the US and in Europe, and they say, hey, why don't you just do what the Americans did or what the Europeans did to eliminate malaria in Africa, eradicate malaria? I mean, you recognize that there is epidemiology in Africa is very, very different. Could you talk a little bit about those differences and why it would take a lot more to control malaria locally than elsewhere?
Well, I think that there are 2 major differences that are highlighted. Of course, one, which we need to go right away, is that malaria, like many other diseases, is a disease of underserved populations. Sometimes it's called disease of poverty, sometimes in developing countries. And so the infrastructure, the capacity to deal with it, the way that people may be living not in air-conditioned homes and things like that, all contribute to it. But the fact of the matter is that in the United States or Europe or in many other countries in the world, the transmissibility. For lack of, we've just talked about R naught. It's an easy way to frame, the approach. It was probably 2 or 3 at best in the United States, and we had a problem. It was 5, in India or Sri Lanka, where they seem to have eliminated malaria. The starting point, the transmissibility in Africa, and it varies, and there are different vectors, and they don't all have the same capacity, but they live longer because of what they are. And the major factor in calculating this transmissibility is how long a mosquito lives, which means can the parasites develop and how many times can they transmit them. And so it's just different. And if we can't labor under the illusion that it's the same thing to eliminate malaria in Kuwait and it is in Tanzania.
In Africa, right. So, Steve, you are one of the most, if you allow me to use this word, one of the most enigmatic scientists, very characteristic. Some people say very animated, but I've read Dr. Fauci's writings saying earlier on that if anybody was going to get the malaria vaccine, it would be Steve Hoffman. You started this very, very many years ago, 1980s, you were already doing these vaccine trials. Talk to us about your journey, Steve. From then, your days in the Navy, your days in the NIH, your work with other enigmatic maverick, Craig Venter at Sanaria, and now at Sanaria. Very briefly, this journey and what we can learn from it as people aspiring to do the same.
Well, I would say that, thank you for asking. It's been an incredible journey. It's been a joy all along, and I would communicate to everybody out there, certainly the graduate students, the students in training, early investigators, that you've got to figure out a way that you love what you're doing, that you get up every day dreaming about first small steps for that day, medium steps, and larger steps. So in the 1960s, I was an undergraduate student, and that was a time of a lot of uproar in the United States and the world, the Cultural Revolution and things like that. And after my 3rd year, I was sitting on a hill. I happened to be actually in Jerusalem, deciding what I want to do in life. And I decided that I wanted to be able to help other people. All right. And I also had now traveled a little bit, decided I wanted to be able to carry around with me what I had in my profession in my head. So I decided I would go to medical school. In medical school, which at Cornell in New York City, now called Weill Cornell, we had the only required course in tropical medicine, as far as I know, in the country at the time. And in that course, this is in our 2nd year, I came to the conclusion that the most people in the world who needed a doctor were ill with tropical infectious diseases. So I decided to become to go in that route. I went from there to a residency in the University of California in San Diego, and a general residency in family medicine, because I thought I might be a doctor living somewhere remotely and needed to be able to handle what came at me. But as part of that residency, I negotiated before I went into it that they would send me to the London School of Hygiene and Tropical Medicine to get what then was about a 5.5 or 6 month course in the Diploma of Tropical Medicine and Hygiene. I did that. Now I came back to University of California, San Diego, University Hospital, and started what may have been the first university-based clinic in tropical and travelers medicine. And it felt like I was a phony tropical medicine doctor, was doing quite well. Had my first son, who is now 42 and is sitting on that motorcycle. I think that if I drove him around on a motorcycle like that now, I'd probably be arrested for child abuse. But that's actually in Bali a few years later. And I went around to get advice as to what I should do, because I wanted to go to the tropics to do clinical tropical medicine. And Professor Nelson, who was at the time at the London School and then later went to Liverpool, said, why don't you go to Indonesia and work with a fellow by the name of Dave Dennis at NAMRU 2. He's doing great work out there. And I said, you know, Professor Nelson, with all due respect, I think that he's in the Navy. And I said that because I had been an anti-war protester, and at the time I had a ponytail and a beard. And he said, nah, I never saw him in uniform. But I wrote to him, and he wrote me back a wonderful letter, Dave Dennis that was, and he was in the Navy. And so I actually then, after about a year of trepidation, cut off my ponytail, cut my hair, took my 8-month-old son at the time, family, to Indonesia to go to NAMRU 2. And whilst I was there, I began working on typhoid fever. And I've done a lot of work on malaria, but my major successes, if we could call them, were actually on typhoid fever. First in a treatment trial of severe typhoid fever, where we showed that dexamethasone, and you may remember dexamethasone has been used to treat severe COVID-19. We were actually able to show in a paper published in the New England Journal in 1984 that it reduced mortality of severe typhoid fever by over 80%. And then we actually did a clinical trial of a typhoid vaccine, TY21A, the oral typhoid vaccine in Sumatra, in 20,000 people in the late 1980s. So we had a lot of work going on typhoid fever, cholera, filariasis, but then I began working on malaria, and it was really interesting, made some wonderful observations, but treating typhoid fever was simple compared to treating malaria. We did studies on high doses of corticosteroids with cerebral malaria. They didn't work. We did a number of other studies. We saw many, many children, particularly on the island of the Indonesian part of the island of New Guinea, which is called then Irian Jaya, now Papua, dying despite all the best efforts of care. And so I came back to the United States after about 5 years and joined the team at Walter Reed Army Institute of Research and the Naval Medical Research Institute, and then what was called SmithKline Beckman or Beecham at that point, which later became GSK. And what you see here in this photo is Dr. Jeff Choulet, who is one of my colleagues then, and is actually still on the scientific advisory board of Sanaria, injecting me with the first recombinant protein adjuvant PFCSP vaccine, which we called FSV1, falciparum sporozoite vaccine number 1 in 1986. In 1987, I was challenged and I had a delay in the onset of parasitemia, but unfortunately, the vaccine didn't work. But we did show in that study a proof of principle that one volunteer was protected by an anti-repeat region CSP vaccine.
Brilliant. Brilliant. Brilliant.
So let me just give one last point to it, so it brings it back to Africa. So at the same time we were studying this, I had suggested that we start doing studies in preparation for vaccine trials in Africa. And so we went to Kenya. Mm-hmm. And I went out to Western Kenya. And at the same time we were doing this, we did a study, which I believe highlights how different malaria is than any other infectious disease. So we took about 100 adults in Saraditi, which is in Western Kenya, treated them for malaria and we used all, including primaquine. We radically cured them of Plasmodium falciparum, and to everyone's really surprise, during the next 4 months or so, 80 or 90% of them became reinfected. Yeah.
So we have a highlight of that study. Actually, we would like to talk about it with respect to premonition.
We'll talk about that later.
Yeah. But I mean, Steve, you've carried that very long distance. So if anybody were to understand the difficulties associated with malaria control, vaccine trials, it's really you. I'm going to stop here and ask my colleague Sheila to move forward.
Yeah, thanks, Fred. Steve, so it's interesting to hear from your story that actually typhoid fever was easier to treat compared to malaria. And given that experience, and given, in your opinion, since we started working on malaria vaccine, developing the vaccine in 1880s, and we are not there yet, we have vaccines for polio, we have vaccines for typhoid fever. So in your opinion, and very briefly, what are the challenges? What is hindering us from getting there?
Well, Sheila, I think everybody on, because of their interest, is well aware of the fact that malaria is caused by a parasite. It's a eukaryotic organism. Humans are eukaryotes. Our cells are eukaryotic cells. They are much larger and more complex than the viruses, which need our own cells to replicate, that cause COVID or polio or dengue or Zika, a number of things you have there, as well as the bacteria that cause typhoid fever or meningitis and so on. So they're different in multiple ways. One, of course, is that they're larger. Their genomes are larger. Their proteomes. They have many more proteins, many more genes. But even more so is in regard to vaccine development, is that they have different stages. Parasites have different stages of the life cycle. So that if I make a vaccine against the spike protein of SARS-CoV-2, and at the first wave, when that virus comes in, I eliminate 95% of the virus with antibodies, but 5% of them get through and they replicate. The antibodies that I made at the outset, first of all, will be boosted by the infection, and secondly, will then work against the next generation and the next generation. In the case of a parasite, which has multiple stages, if I make antibodies against the CS protein, the mosquito injects 100 sporozoites, and one of them gets through in a non-immune individual, a week later, there'll be 50,000 parasites in the bloodstream, and the antibodies against the CS protein don't recognize them. So it's a very different mechanism by which we have to work. And if we're working at the pre-erythrocytic stage, then we have to get all of them to really have the sterile immunity we're interested in. We know from RTSS, R21, and so on, that we don't have to get all of them to have an impact on clinical malaria. But it's very different than a virus or a bacteria.
Thank you very much, Steve. That's very, very clear. Fred?
Yeah, I'm just going to ask Ali if he has a follow-up question on this.
Thank you, Fredros. Thank you very much, Steve. So my question, Steve, would be with regard to the long journey that we had to go through for malaria vaccine, and until now, despite having quite interesting and potentially good vaccines, do you think that our lack of understanding of what malaria immunity is really has contributed in the delay to come up with an effective malaria vaccine?
So great question, Ali, and the answer is is not black. It's not 100% one direction. The answer is yes and no. All right. If we go back to and say, let's talk about RTSS, right, and how that vaccine was developed. So the way that was developed was that initially it was shown that mice and people could be protected by irradiated sporozoites. And then it was thought that mechanism of protection was through antibodies. And then it was shown in 1979 and 1980 by the Nucleic group that you could make a monoclonal antibody against the what they discovered to be the CSP, the circumsporozoite protein, and later showed that it was against the repeat region. And then if you passively transfer that monoclonal antibody, that you could get protection. So then we went to FSB1, what I just showed, which was directed against those repeats. And subsequently, a few years later, it was actually in 1988, the concept for RTSS was conceived. And now we are 35 years later or so on, making the highest level of antibodies of any vaccine in the world against the repeat region of the CS protein, probably 10 to 100 times higher. And again, I haven't seen the exact numbers than we make with the RNA vaccines against SARS-CoV-2, and getting good protection, not the best. So from there, we actually have a 40-year history, or maybe 50-year history of going forward with something we did know about. Now, the problem is what we don't know about. So it turns out, and I think we're going to talk about it later, that irradiated sporozoites don't primarily protect through antibodies against the repeat region of the CS protein. They can provide better protection than just the recombinant protein vaccine, but they are against they make tissue resident T cells in the liver, which are very hard to study, and we still don't know what their targets are. So after all of these years, we have some, but we don't know everything. We can take that discussion to the blood stage also. You're working on RH5 at the moment. We only discovered that 10 years ago or so. And at the sexual stage also. So the answer is that for this very complex parasite, which varies itself also, we have a lot of knowledge, but not enough. Having said that, a lot of vaccines were not developed based on understanding everything about them. It was done empirically, but they weren't the complex eukaryotic cells with different stages that malaria parasites are.
This is great, Stephen. When we will, it should be nice at some stage during this masterclass that we talk about this and early as well, the variability on the parasite side, but also the variability on the red blood cell surface.
And the variability of the human host.
The variability of the human host,
can make a different type of response.
Right. So, but that's coming up soon. So let's go back a little bit and talk about the big picture. This is our colleagues at PATH do a lot of work together with the WHO and the vaccine trial community to put together, a global picture of where we should be going and so on. And this is a 2013 malaria vaccine technology roadmap. I believe this is still valid. We don't have an update of the horizon here, but Dave Schellenberg and colleagues at WHO are trying to figure out if we can get an updated version of that. Steve, in this version, the aim appears to have always been to get something that is at least 75% effective. Talk to us about this threshold and why it's important to achieve that high before we can really call it a good vaccine.
Sure. So this was the first threshold. This malaria vaccine technology roadmap started in about 2006, I believe, and the threshold was actually 50% reduction in severe disease and death. And then in 2013, it was changed to this. So if we just go back to the first threshold, it's not clear that we've achieved the first one. Now we're on to the second one, all right? Be that as it may, and we hope that the implementation studies with RTSS will actually give us an indication that maybe we have achieved the first one eventually, which is death. So now we have come with the second one, where the vision was 75% reduction in clinical malaria. And We all saw that there was one study on R21MM, which was published a month or so ago with a tremendous hoopla, that showed that that was achieved, at least in one trial, with seasonal malaria in Burkina Faso, in a place where, if we looked at 6 months, immunizing just before the transmission season, we may actually have seen the same thing with RTSS. But the question is, is there some magic number about 75% reduction in clinical malaria? No, I mean, I think it's an arbitrary number that all of us would agree that if we could get a 75% reduction in clinical malaria.
Sorry, Steve, we unmuted you by mistake. Just unmute yourself, please.
I don't know where where do we?
Yeah.
The issue is, is 75% some magic number? If you get 75%, is that going to give you quote unquote herd immunity? We hear about that all the time with COVID-19. The answer is no, because we're talking here about clinical malaria. We're not talking about infection. We're not talking about transmission. We're talking about reduction in clinical malaria cases, which can be associated with reduction in the number of parasites, not necessarily even whether these kids are infected or not. So it's a good number. It makes a lot of sense, but I don't think there's any magic around it. It's a good target. One needs to have goals and targets to go after.
Thank you. Thank you.
Yeah, Steve. So that's actually interesting, and given the threshold. So given the interventions that we have in place, that we currently have in place and are working, and eventually if we happen to have a vaccine that is effective, where do you think it will fall? How would we be able to integrate it so that we are working in an integrated manner with all these other interventions?
So initially, and particularly because of the epidemiology, which is changing. So we have a moving target, first of all, that the incidence rate in different age groups has changed. The burden of disease is moving towards older children from younger children because of the success of some of the other interventions. But originally, the idea, I believe, with RTSS, and I wasn't involved with it, was to be able to have a vaccine that could be used in infants, young infants, under 6 months of age in the EPI, and just fit in with the other EPI type of vaccines. And unfortunately, that group wasn't as well protected with RTSS as older infants and young children. And so the recommendations were, and the current implementation studies are, to study it in 9-month-olds, all right? Because you have to, I mean, one of the things I think that's quite instructive about the whole process that we've seen with RTSS is that we're up against a formidable foe. We shouldn't be boxing ourselves into, it has to be 50%, it has to be 75%, it has to be in this age group. RTSS, as far as I can tell, didn't meet the first guidelines, all right, in terms of severe malaria and death, but it had a good positive effect. So it was taken forward into the next round of studies, but not in the originally envisioned age group. But fortunately, it was tested in an older age group, and it seemed to work. So now we have a vaccine that's going forward that hopefully will end up being implemented in 9-month-olds in an EPI type of setting. And that, if you give that every year to 9-month-olds, and we boost it at 20 months, and we boost it again perhaps later, we should be able to, over time, make a significant impact. We also are going to see data coming on the vaccine used in the Sahel of Africa, where there's seasonal malaria, and where you might be able to give it every year. And whether that's RTSS, R21, or our vaccines, if you gave it in the dry season and then boosted every year just before the rains in many different age groups. In the way that we give SMC, we give intermittent treatment to groups, whether they be young children, I think we'll be going to school-age children. That's our goal at this point. Or pregnant women, you have another group. The area where we really would like to see the vaccine implemented, and what we've been focusing on, is the idea that you can immunize the entire population in geographically focused locations to halt transmission and eliminate malaria from that, eliminate transmission. So those are three different types of settings. Now, on top of all of that, as we limit malaria in Africa, let's just talk about Africa right now. You live in Nairobi. There's really no, maybe with climate change, there may be some transmission, but there really is little transmission in Nairobi. If a child grows up in Nairobi, they're no different than a child growing up in New York in terms of their naturally acquired immunity. And if they happen to have grandparents who live in Kisumu and they go down to visit, they are just as much a risk as if I brought my children from or grandchildren from the United States. And so now we're going to get into something what we often have called traveler's vaccine, but it's actually going to happen in Africa also. There's a great need for that. That's a whole nother population that nobody's really talked about. So those are four different populations, Sheila.
Ali wants to bring up an issue on this as well. Sheila, sorry I interrupted you.
No. I just found the age-specific issue about vaccines really interesting. And I was wondering if, Steve, you would probably briefly elaborate why, for instance, for RTSS, we have to specifically work with 5 to 17 months?
Well, the reason why it's 5 to 17 months is because it didn't work as well in 2 to 6 month old, 2 to 4 month or 6 month olds. So if you immunize the younger infants in the phase 3 study, they didn't do as well as those that were 5 to 17 months. And then my understanding is that SAGE from WHO recommended that it be used in around 9 month olds, which is why it's being done in that kind of way in the implementation studies. So it was actually being responsive to data that, okay, let's not push something that's not as good and let's go to where it could be better. Because we need success.
Thank you. That's interesting. So because it hasn't been tested in adults, it can't be used in adults.
It has been tested in adults. There was a study done in Kisumu in adults in which RTSS AS01 did not have significant protection. But it hasn't been studied extensively in adults. The first study in Africa was actually with RTSS AS02 in the Gambia, and it did have very modest efficacy for a short period of time that went away. So it may, and that was one of the reasons perhaps why it hasn't been further studied in adults.
Yeah.
Cool.
Thank you, Steve.
We're going to move forward because of the time, and then we'll come back to Ali. Steve, very quickly, in 2011, and I believe you participated in this process, a group of scientists came together and built a research agenda for malaria vaccines. And this concept of vaccines that interrupt transmission came up.
Sure.
This has been reiterated in the 2011 version, in the 2017 version of the malaria refresh. Now, in the past year, of course, we've been dealing with the COVID. We have some lessons from there. One is that, you can actually do very well if your vaccine just prevents severity, even if it doesn't prevent infection that well.
Right.
And we see this also with the HIV treatment programs. In general terms, and from a technical perspective, do you think the targets for malaria vaccines will change going forward based on the lessons we've had from COVID?
So if you look at the guidelines that you just showed me, the roadmap, the original roadmap, the primary objective was reduction of severe disease and death. So not just like number 1 that you have here, And I hope that the implementation trials that are going on may give an indication that that's the case. All right. So that's not changed. And again, that always has to be our first goal, is to reduce severity and death. Then we have the idea of VIMS, vaccines that interrupt malaria transmission. And there's two approaches to that. One is what people in the past have called transmission blocking vaccines, meaning vaccines against the sexual and mosquito stages of the parasite life cycle. The prototype has been PFS 25, PFS 4845, PFS 230, and so on. And there's work going on in that. One of the problems with that approach is that the individual that works for the community, not for the individual who may or may not be infected, will have no effect on the severity of illness in that particular individual. The other type of VINT is the pre-erythrocytic stage vaccine, because if you prevent the parasites from ever getting out of the liver into the bloodstream, not only do you prevent bloodstream infection and all clinical disease, but you also prevent transmission. So our approach has been to focus on a highly effective pre-erythrocytic stage vaccine, which would take care of all three of those. Now, in the event that you're not perfect, you might like to have a backup. So we have Ali's working on RH5. And if that happens to work against reducing severity of illness in the blood, that would be a good type of addition. And then we have groups working on PFS 25 and others, and that would be a good addition to it. But if we can achieve really good success with a pre-erythrocytic stage vaccine, we're way, way, way ahead of the game.
Thank you. Ali, please.
Thank you, Pedros. I wanted to go back to the earlier question related to integrating the vaccines in malaria control programs. And I wanted to ask Steve about, we are already spending a lot of money with these other tools. And we have always been thinking that, the vaccines they're going to complement the existing tools to sort of control and eventually eradicating the disease. But someone working within the program might want to know if we have very good vaccines, are we looking to the future where we won't have to use these other interventions if the vaccines are working very well? Or should we always envision that we would have vaccines alongside these other tools for foreseeable future?
So the answer to the is yes and yes and yes and no and no and no. So again, we have the epidemiology. Malaria is not just one disease from an epidemiological point of view. And so that in some places, the answer would be, we got a long road ahead of us, and we're going to have to be hitting malaria with every tool that we potentially have. And in other areas, we may actually be able to get to the point of even, elimination, limit transmission, in which case, if you have a vaccine that prevents reintroduction, you wouldn't need to have to use all the other tools. And Ali is well aware of the fact that working on Bioko Island in Equatorial Guinea, where there's a very intensive malaria control program, perhaps one of the most intensive in the world, we've mapped out how one could add a vaccine to that, eventually get to the point of knocking out transmission and elimination, and then just try to prevent reintroduction with a vaccine. So it really will depend on the situation. The Boston Consulting Group, quite a few years ago, at the behest of, I think, Path MVI, did a study that indicated that if we did have a successful vaccine, we would be able to cut tremendously the costs of malaria control efforts. So that in the places with most intense transmission, we have to be envisioning keeping at it for a number of years. But as we begin to knock out malaria in different places, one certainly could envision, if you have a very good vaccine, eventually being able to cut down on and even potentially stop all the other types of interventions.
Excellent. Excellent. This is really, really nice, I have to say. And dear colleagues, kindly mute your microphones if you're not speaking. Steve and Ali, I just want to say this is really, really nice to hear you guys talk about this, especially given your experiences working in both East Africa and in Equatorial Guinea. And I hope that more of this can come up as we move forward. I have a quick question for you, Steve. Would you mind if we go back to some basic immunology for my colleagues who are on the call who are vector biologists?
Sure.
Okay, so very, very briefly, some basic immunology here. This is, a nice review done by a group from Oxford on vaccinology in general, different types of vaccines shown over there. But can you just comment on these terminologies? What does it mean when we say live versus attenuated, an adjuvant, immunogenicity, innate versus adaptive? Very, very briefly, just to help with our colleagues who are not vaccinologists.
So vaccinology began with the smallpox vaccine with Jenner, right? Which is a cowpox, which is a live virus. So that's a live vaccine. It's not attenuated, weakened, or inactivated. It's actually just a different virus. It's a cowpox as opposed to smallpox that the immunity cross-reacted so that it couldn't cause disease in people. It does actually in 1 in a million if you're immunocompromised and so on. So that is a live whole virus vaccine from a different type of virus. We then go forward and let's just take polio, all right? So we have the oral polio vaccine, but the first vaccine was actually the Salk vaccine, which was an inactivated polio virus. So now we go to a killed, it's not an organism. A virus is not an organism. I mean, it's an infectious agent, but that's a killed vaccine, right? And many, but most of the vaccines, then we have live attenuated. So then we take something like a measles virus and it's passaged in vitro in culture and it becomes attenuated. And it doesn't cause disease, but it causes a protective immune responses. So now we have a live attenuated or weakened, vaccine. And then if we take sporozoites as another example of a live attenuated, but there it's metabolically active but non-replicating. Many of our live vaccines actually do replicate, but then they stop, right? So that, if we go, that's number one and number two. Then we have a toxoid vaccine. So in 1920s, there was the introduction of tetanus toxin or toxoid vaccine. And there we have, and also for diphtheria. So there you take the toxoid, or toxin of the bacteria, isolate that from the bacteria and use that with an adjuvant. And in that case, it was aluminum hydroxide, which was introduced in the 1920s, and until recently was the only adjuvant that we actually had. So now we have a toxoid vaccine. Then we come to subunit purified protein, recombinant protein, and polysaccharide peptides. That's a big mouthful. So if we think about let's just talk about recombinant protein. In 1986, the hepatitis B surface antigen vaccine produced in yeast cells, where the surface antigen was expressed, was put on the market as the first purified recombinant protein vaccine, also administered with an adjuvant. That's the hepatitis B vaccine. Then we have polysaccharide vaccines. Some of the first polysaccharide vaccines were Haemophilus influenza, typhoid. So there was a VI vaccine. We now have a VI conjugate vaccine, but where you grow the bacteria, you isolate the polysaccharide, you purify it, you give it generally with an adjuvant, and you have a vaccine like that. And then we have virus-like particles, which is a human papillomavirus vaccine, where it's still, again, a recombinant protein, but it comes in the form of a virus-like particle. Now we have a big development. So if you look down there at protein polysaccharide conjugate, all right? So in the case of, the biggest example is, say, pneumococcal vaccine, which is the largest, until recently probably, but with COVID, but the largest selling vaccine in the history of the world, where initially 7 different polysaccharides from 7 different strains of bacteria were conjugated to a carrier protein and then given as a vaccine. Because if you just give the polysaccharide by itself, you have to give it frequently, and it's not so immunogenic, and particularly in children. Now we come to viral vector. Now we're really starting to get, and I would just say that in many of these kinds of vaccines, malaria actually did lead the world. But if we think about the AstraZeneca or the Johnson & Johnson SARS-CoV-2 vaccine, we have, in the case of Johnson & Johnson, it's an adenovirus. It's called adenovirus 26. In the case of the AstraZeneca from Jenner, it's a chimp adenovirus in which you engineer the spike, the nucleotides that code for the spike protein of SARS-CoV-2 into the adenovirus. You inject the adenovirus, and it goes into our cells and then produces that protein in our cells. So that's a viral vector vaccine. We've been working on those for decades. And some of the, as I said, some of the first work was actually done on malaria in the 1990s on this. We had that for Ebola vaccine also. Now we come to nucleic acid vaccines, and really, Pfizer's vaccine, Moderna's vaccine, CureVac in Europe is making that. And I can tell you that the first nucleotide vaccine, the first nucleic acid vaccine.
Sorry, Steve, we unmuted you by mistake. I'm sorry about that.
Are you trying to get rid of me?
No.
So
I was trying to get rid of someone else. Go ahead.
Okay, so let's talk about nucleic vaccines, all right? So the first nucleic acid vaccine, so we have nucleic acid are DNA and RNA vaccines. The first nucleic acid vaccine ever given to a normal human being was a malaria vaccine. It's a CSP DNA vaccine. I actually administered it, and our publication on it until recently was the most highly cited publication on any nucleotide vaccine until we just got to SARS-CoV-2. And that was the predecessor of RNA vaccines also. So that's nucleic acid, but malaria was actually there first. The problem is that the magnitude of the immune response that you need for malaria is so much higher than it is for a virus that it is not adequate. Bacterial vectored vaccines, I don't know, I'm blanking at whether we have any that are licensed, but in our team at Sanaria and Protein Potential, for example, we've made vaccines where TY21A, the bacteria for the typhoid vaccine, is engineered to express proteins from Shigella sonii. Yes, so we just had a cholera vaccine license. That's a bacterial engineered vaccine, but we're making TY21A that expresses enterotoxigenic E. coli immunogens, Shigella immunogens, and now we've made SARS, spike protein, M and N protein. So that's another way of doing it. And then antigen presenting cells, again, I don't believe that's really being done for cancer, all right, where you actually can take people's cells and engineer them to express targeted proteins. So it's a vast array, and really in the last few decades, we've made unbelievable progress. So I think we'll be seeing as we go forward a lot of these new approaches. But taking it back to malaria, we have the beauty of the nucleotide vaccines is you can, the reason is you can make them fast and you can make a lot of them. And so that would be beautiful if we want to have a multi-stage malaria vaccine. And we actually came up with something called Must Do 5 and Must Do 15 in the 1990s, where we put everything in there, every single stage. But Then you have to get to the magnitude of the immune response, which malaria requires something completely different than the viruses or bacteria for which we have vaccines.
Thank you, Steve. Thank you so much. Thanks for the overview. I just also, for my colleagues who are not vaccinologists, I hope you guys found that useful. Continue.
So I just want to make one more comment.
Go ahead, please.
Sitting here on the verge, we have the implementation studies of RTSS. We're beginning to see some protection. We'll see 100% protection, I'll tell you about, published in a few weeks against heterologous parasites by one of our vaccines. Malaria scientists have been working for the last 30 or 40 years at truly the cutting edge of vaccinology. And many of the things that we're seeing introduced actually really were first assessed in humans in malaria, in part because we have the controlled human malaria infection model.
We actually have some questions coming up on that as well. So more specific, and we have questions on the chat also from people on that. So that's going to come up as well.
Or do you have, should be able to enter your passport.
Sheila, please. Go ahead.
Yeah, Steve, I think you've mentioned very briefly that a vaccine that attacks all the stages, that targets all the stages of the malaria transmission cycle. Did you say that would be ideal? Or rather, which is the best stage to target? Is it the pre-erythrocytic stage? Or in your opinion, which one would be the best?
So, Sheila, ideal would, of course, be every stage, all right? And as I said, in the 1990s, we came up with a wild scheme to actually do that. And others are now trying to approach that yet again. But if you had to pick one stage that you would go after, it has to be the pre-erythrocytic stage, because if you prevent parasites from and if you pre-erythrocytic means that you prevent the parasites from ever getting into red blood cells. If you prevent them, it'd be better to say that, it's actually preventing them from ever getting out of the liver into the bloodstream, because if you do that, you can't have clinical disease and you can't have transmission. So that would be the most ideal, particularly if it was 100%. Now, if it's not 100%, then you'd like to have some backup. And that's why I was saying earlier that if one had a vaccine against the blood stages where there's this incredible amplification, and that's what Ali is working on, for example, with the team from Jenner of RH5 that ameliorated, reduced the impact, even if you do get a blood stage infection, that would be great. And then if on top of that, you were able to reduce transmission, so, with another vaccine. So think about this. If you had a blood stage vaccine that was 90% protective, and you had a mosquito stage vaccine that was 90% protection, now you have more than 99% protection. Now you're really talking about something. So we have to be cognizant of the fact of this multi-stage parasite with incredible amplification in the bloodstream. Every 2 days, we have a 10 to 20-fold multiplication of the parasites. So you need to prevent that, or if you do have it occur, you have to prevent it from going forward.
Thank you. Ali, go ahead, please.
Yes, so Steve, just as a follow-up question, maybe I would like you to comment on two important issues which are often being discussed within the malaria community. First of all is the duration of the vaccine efficacy. What would you say is sort of an ideal? And the second point is the ability of the natural exposure to sort of boost the responses of the vaccine. What can you say about these two components, and what are some of the issues that vaccine developers should think about with regard to these 2 points?
Okay, so ideally a vaccine, the ideal vaccine is a single dose that lasts for your whole life, right? So having said that, I would go back to the epidemiology of malaria and talk about what populations you're interested in protecting. If I'm interested in protecting Sheila's children in Nairobi who go to visit grandma and grandpa in Kisumu, then I need a vaccine that works for a few months and I can boost it every time they go, give them a shot. If I'm interested in protecting children, pregnant women, any individual in the Sahel of Africa, Mali, Burkina Faso, where there's only transmission 6 months of the year, then I could really come up with a strategy where I could get a vaccine, get full, protection before the transmission season, and then boost every year. If I'm on Bioko Island and I want to halt transmission, we can do modeling that indicates that if you were able to immunize the entire population, give them also mass drug administration at the same time, that you might be able to actually eliminate the parasite. You then have to interdict it from coming back in, but you might not need, you might have to keep boosting, but you might not need to have long duration. But having said that, from a practical point of view, with 1 billion people in sub-Saharan Africa and so on, you'd love to have a vaccine that lasts for long periods of time. So that's the first, and I think that we need to take this in stages because we really have a formidable problem, and that there's nothing wrong with conceiving of initially more frequent boosts than we might have with other vaccines. We get to the issue about boosting of of vaccine-induced immunity. It's hard to know. All right, you're dealing with an antigen that actually doesn't boost, right? I mean, RH5 is designed not to, be able to be boostable because you don't really have, naturally acquired immunity to it. We know that you don't get much boosting if of CS protein antibodies. It just doesn't. We're having to make a level of antibodies that's so high that you don't get boosting with it. So I don't know of a lot of examples of boosting. We do know, if we believe that protection against severe disease is due to immunity against many different VAR genes and so on, then there's probably some boosting there in terms of clinical immunity against severe disease as you grow up in a malaria endemic area. But what happens when you start reducing that, we don't know. So I think that we have to start with what we have and then move forward systematically over time.
Thank you. Thank you both. Thank you both for this. And I think we're going to come back to many of these questions, and we should actually come back to that, especially the issues about pre-exposure and the immunity. That should be nice to hear from you and Ali on those issues. Steve, one of your, I don't know about you, but if you're looking for a comprehensive analysis of vaccine candidates, one paper that we found very interesting when we were preparing for the masterclass was this review that you did with Richie and Patrick. And here you describe 4 different vaccine classes, the RTSS, of course, the prime boosted DNAs, and the recombinants. And I would like us now to start a journey here, starting with RTSS, and go through this journey briefly and end up with the sporozoite infection vaccines to really get the technical details out. So back to RTSS again, most advanced vaccine. One thing that we notice here is that even though it's always said that the protection was fairly small, there were places, sites of the trial where protection was actually quite high, such as you see down there in Kilifi. The other thing that you see is that in terms of the number of cases averted, you can get, in some places, very high number of cases averted, and especially if you have boosting, but it doesn't work with children. In your perspective, and this is related to the question we asked earlier, in the design of future vaccines, should this be the new standard to compare everything against? And how so? So just some highlights on how we interpret these values in terms of implementation. I know that the RTSS implementation team is working a lot on the basis of the fact that it prevents cases and averts deaths. But in terms of future vaccines being developed, how should we compare them to the RTSS going forward? Back to you, Steve.
So the answer to that question is, again, multifold. And a lot of information is going to come out from the implementation campaigns and what they actually show. So I can't really comment on that because I don't know what actually they have shown, and then we have some other studies that have been done, which I think are going to highlight how it might be used in the Sahel of Africa and SMC in under fives who are taking, or under sixes who are taking SMC. But from the data that we have, and let's just go back to why with all the data, with the positive opinion by the European Medicines Agency in the Article 58 and the opinion, why did SAGE not recommend going forward with anything other than an implementation campaign? And the answer to that, and which really has to be looked at, is there were some safety issues that arose with the vaccine. And we have to understand that the balance between safety, tolerability, safety, and efficacy always has to be taken into account, right? And we've seen that a lot, particularly in people with COVID-19 vaccines who don't want to take, they don't want to have a fever for 6 hours after their second dose. They're afraid to have it. We're going to see that even more so, by the way, with boosters, right? But I believe that most of the parents in Africa have been much willing to accept the fact that it actually hurts, right? So the tolerability of RTSS, there's a high incidence of pain, crying, and a statistically significant increase in febrile seizures in the week after you receive RTSS. So that's one thing. Wouldn't we like to have a vaccine that doesn't hurt? Babies don't cry and they don't get seizures, right? Secondly, we had the issues, if you didn't give a booster, you could have increased cerebral malaria. You have one group, which is quite prominent in the vaccine world from Johns Hopkins and a group in Australia that made an analysis that females actually had double the mortality of the control group. And there was many exponential explanations for that. We had a 10-fold increase in meningitis, albeit with small numbers, right? But nonetheless, so these are all things that's one side of it. You have to look at, would you like a vaccine that is better tolerated and doesn't have some of the safety signals that were at least identified? We're going, the decision was made that it was okay to go forward because of the potential positive outcome, and because some people didn't think that maybe they were that important. But a lot of people have thought that it's very important. And so we just have to see, and hopefully we'll know a lot more soon about that. Now we come to the efficacy, and that's really what you're asking me about, is efficacy. And, this is not fantastic efficacy, but it is efficacy against thinking about, we have one protein, and it's probably, the majority of it is antibodies against the repeat region of the C. One protein out of 5,000 is giving us a sustained level of efficacy, albeit at extremely high levels, but at levels that are better than not. And if you have 200 million cases, if you have 500,000 deaths, and let's just say that this actually did translate to deaths, and you had 30% efficacy against more severe disease and death, 30% of 500,000 or whatever it might be in Africa, is a lot of lives saved. So we have to put it in that context. And so the answer is, on all of those fronts, we would like to get improvements or additions to the efficacy we're seeing here. And that's what the next vaccine should be looking at. And they also have to look at the broad brush of epidemiology that I mentioned, that it's not just one homogeneous epidemiology or disease. It varies from place to place and so on.
Thank you. Steve, a few weeks ago, we spoke to Professor Greenwood, and he told us about the studies they were doing in West Africa, in Burkina and Mali, I believe, where they have this concept, and you mentioned it already there, the concept of seasonal vaccination. I would like, together with my colleagues here, to get your thoughts. And I heard you mention this a little bit earlier on the practicality of this. I know that there are studies about being published. I don't know which journal. I suspect New England Journal, but we haven't seen the results yet. This is just a description that Brian provided earlier. What are the practical implications of seasonal vaccination in the place where you are already implementing seasonal malaria chemoprophylaxis, for example?
So we know that with seasonal malaria chemoprophylaxis, we don't eliminate infection, we don't eliminate disease. We have it works very well, but this is one of the situations where if we had a really good vaccine, this is what Ali was talking about earlier. So one of the interventions is just seasonal malaria chemoprophylaxis. If you had a highly effective vaccine and all you had to do was boost at the beginning of the transmission season, you could eliminate having these kids take seasonal malaria chemoprophylaxis. For right now, the studies have looked at it, the combination, and we'll see what the results come out in papers that are being, paper that's being reviewed right now. But the what I understand is that it looks pretty good. And so, again, we're on a continuum here, right?
So how exactly does it work? How can you explain the process?
Okay, so let's just say that you go back to the life cycle and RTSS, it may not be correct and people may argue with me about this, but let's just say that all of the immunity of RTSS is against the repeat region of the CS protein. And there's no Plasmodium falciparum parasite in the world that doesn't have the same essentially repeat region. NAN, asparagine, alanine, asparagine, proline, and then there's some variant repeats, but the primary repeats that. So you're making antibodies against that. Those antibodies are there before the child ever sees a infected mosquito in, let's just say mid-June of every year when it starts raining, mid-June to July to August, and they prevent the infection. Now, if you can prevent the infection in entirety, you don't need any SMC. The fact is that RTSS is not a perfect vaccine. It's the onslaught that one sees during that time is stupendous in terms of the number of infected bites that kids are exposed to. So that's why it's being studied, in combination right now. So that would be the idea, is that you fully immunize 1 year when the child is 1, 2, or whatever, and then you give them a single booster would be the ideal prior to the transmission season, and that should protect them. Now, whether that's the case, we have to see, and we'll have to do a lot more work in terms of that. We're envisioning that. We're starting a study in Mali in a few weeks in a little bit older children, because they actually have an incidence rate which is higher. And we'll be looking at the same thing.
Cool. On that note,
Yeah, Fred, I think we covered this one.
Well, let me just tell you about this, just a little other comment about this quickly, is that adults who have had lifelong exposure to malaria have what we call immune dysregulation. I may talk about it a little later if we talk about our vaccines. The immune responses they make are 20 to 30 times lower than adults in the United States and Europe to the exact same immunization regimen. So immunizing effectively adults in Africa, we now have 5 studies in which we've done it, but the protection we're seeing over 6 months is about 50%. 57% tops, which is much lower than we anticipate we'll have in children in a similar setting. And it's because they don't make good immune responses because they've seen malaria. It's almost like they're desensitized. It's like you went to an allergist for a bee sting allergy. You get bitten by a few mosquitoes today, another day. So that makes it more difficult for adults, but we know we can protect adults.
Okay. So before we proceed, before we proceed with this, so the infants at very early age, it's not so good, and as adults in endemic countries, also not so good. That's what you're saying.
Yes.
Okay. Cool. Ali, please.
Thanks, Pedro. So, Steve, I wanted to bring another concept or issue that normally faces malaria vaccine development, and that is, especially we've seen this with the blood stage malaria vaccines, is the issue of strain-specific protection. So, whatever you give the volunteers or the vaccinees, you get protection or sort of homologous protection to that strain that you've developed your vaccine. And we've seen this with mostly, as I said, blood stage candidates, but we've also seen it with subunit pre-heterocytic vaccine, RTSS. How can you, what would be your comment about this, and how whether this would be an impediment in the effort to develop an effective vaccine for Africa?
So this is, of course, we could sit and talk about this for the next few hours. One of the reasons why you're studying RH5, for example. And it's one of the reasons why, not to belabor what I said over and over again, why RTSS works is because it makes antibodies against a region that is completely invariant in the parasites. Now we come to one of the problems with blood stage vaccines is, of course, exactly what you're saying is that we'd love, the major hypothesis is that VAR genes are responsible for cytoadherence. They're responsible for severe disease. And as such, if we could make, antibodies that prevented cytoadherence, the parasites would be taken out in the spleen and we wouldn't get any of the severe disease of Plasmodium falciparum malaria. The problem, of course, is that we have 59 to 60 copies of the VAR genes in the genomes of any Plasmodium falciparum, and then if you go from one to the next, those copies vary from each other, and so that you have a sort of unending repertoire. And we know that in people who do live in endemic areas and don't die of malaria, that eventually they do develop significant clinical immunity, in large part perhaps because of having antibodies that cross-react with many different VAR genes, as well as many different proteins. There was a study done on an AMA1 vaccine in Mali a number of years ago, in which the team showed that they actually did have some protection, and they claimed 65% against the sequence that was in the vaccine, but there was no significant protection when you took it against all the parasites out there. So it's a huge challenge at the erythrocytic stage level, depending upon the vaccine. There was great efforts initially to make vaccines against the two different alleles, C-terminal alleles of MSP1, major surface protein 1, but they somehow, that's not really been pursued very much recently in the last decade. And the pre-erythrocytic stage, initially, and I'll talk about this a little bit later, with the CVAC approach, the chemoprophylaxis with sporozoite vaccines approach, it seemed like there wasn't protection against heterologous parasites that differed from the vaccine strain, but we've shown that by increasing the dose of sporozoites that we can overcome that, but perhaps by invoking higher levels of immune responses against what we call subdominant epitopes that you might not make a vaccine response against, at dose A, but if you give 5x of that dose, you actually do begin to make responses. But we know very little about the specifics of these mechanisms, and it's really an area that we need to study much more.
Thank you.
Let me just add one thing.
Go ahead.
One of the things that was most striking to me, and we haven't done that much work in this arena, particularly at the blood stage, but 25 years ago, we kept giving aotis monkeys a particular strain of Plasmodium falciparum to the point where initially they would die if you didn't treat them, and then they would get very ill. Took about, after 5 doses of the same strain, the monkeys had sterile protective immunity. There was no parasites that you could find. We then challenged them with a different strain of Plasmodium falciparum, half the monkeys developed life-threatening anemia. They all became. So you can drive with a single strain immunity to complete sterilization. At least this was in monkeys, and I believe it's probably the same in humans, and completely overcome that just by changing to another strain.
And Ali, is that okay? You have a follow-up question, or we proceed for now?
I think we should proceed, because I'm sure Steve is going to talk about more when we touch on the PFS. Yeah.
Indeed, and Steve, we have lots of questions also on the CVAC approach, which we find very interesting. Now we're going to talk about the Sanaria portfolio, a very innovative approach, focusing squarely or mostly on whole sporozoid vaccine candidates, and developing also a range of other products that you have. This information is, of course, from your website. But this story begins a long time ago, and I want to take you back to Saradidi, which is not very far from where I was born, and where Shaila's mom lives today. You did a very interesting story there in 1987. I think this was published in 1987, where you demonstrated that naturally acquired antibodies, you talked about this earlier, naturally acquired antibodies do not prevent malaria. Briefly, before we proceed into the Sanaria portfolio of work, how the lessons you had at that time about the implications of this on malaria vaccine development, back to today, up to today, what take-home message do we have from that? Has there been any changes in this science, or is it updated? Is it still the same?
So this was, thanks for bringing this up. So what happened was that we were proceeding very rapidly with development of sporozoite and CS protein vaccines. And it wasn't just FSV1 with aluminum hydroxide as the adjuvant. All the adjuvants that we've talked about we were studying at the time. And a year later came up with the idea with Joe Cohen and the team from GSK about RTSS. But I had published a paper a year earlier in the New England Journal of Medicine, from looking at antibodies, naturally acquired antibodies in different age groups in Indonesia, an island called Flores, and shown that there was a correlation between age and antibody level, and age and incidence and prevalence of malaria. So the natural assumption is that because we have more of these antibodies and we have less malaria, that we actually, as people get older, that there's an association and there might be a cause and effect. But that was not the best way to do this. So we designed this study. I designed this study to go to Kenya, to Saradidi, and just as an aside, many of you will know Chris Plow. And Chris Plow was at that time a 4th-year medical student at Cornell. And he had actually 2 years earlier worked with me on a cholera treatment in Indonesia. But Chris actually went out to Saradidi and convened a meeting with the town elders in the middle of the street, between the houses there, to go over this study and explain it to them. And in any case, we did this study where we took about 100 individuals and radically cured them of malaria. These were adults. And then over the course of, you've seen 98 days there, 78% of them developed a repeat infection by a thick blood smear. And we looked at the antibodies by many different assays: ELISA, IFA, inhibition of sporozoite invasion, functional assay, circumsporozoite precipitation reaction, which nobody does anymore, to see if there was any correlation between either the 25 or 22% of the people that didn't get malaria during that time and the 78% that did. The assumption, the hypothesis being that those would have higher levels of antibodies, or in the time till they actually took to get infection, and there was no difference. And so at the same time as I was being immunized and challenged and getting malaria from the first CS protein vaccine, I published a paper that was entitled "Naturally Acquired Antibodies to Sporozoites Do Not Prevent Malaria." Now, what we said in that abstract was that if we were going to get antibodies against the CS protein that were going to be protective, they had to be a lot higher and more functionally active than were the antibodies in the people out in Western Kenya. Yeah. And so that was a very important study, but it also provided a foundation for going on to another study 2 years later, which showed that what we really needed was tissue-resident T cells, not antibodies. Didn't mean that antibodies couldn't work, but that what was happening with irradiated sporozoites and sporozoite exposure was tissue-resident T cells. But this shows that there's very little sterile protective immunity in the field against malaria.
So this I've seen, I believe last week, I haven't read the paper itself, but it was in the news somewhere about where we should be looking for T cell responses against SARS-CoV. And turns out that these tissue-resident T cells may be much more important and a better approach than that. So any guidance on that at a later stage might be helpful. Steve, let's move now to PFSPZ. I believe that's the right pronunciation.
Yes, not Z.
PFSPZ. At Sanaria, you work on 3 different options. Vaccine that is irradiated. You have a genetically attenuated. You also have the CVAC approach. I don't know. I mean, I'm going to ask Ali to coordinate this specific discussion so that our colleagues can understand this much better. Ali, please.
Thank you, Pedro. So, Stephen, to start with, I wanted to again take us back to the early, I think, 70s when there was this demonstration that 1,000 irradiated mosquitoes can confer sterile protection, and I think this was a great important milestone that provided the foundation for the development of the pre-specific malaria vaccine and RTSS and the PFSPZ vaccine itself. However, many times I've heard you say, I mean, at that time, most people actually thought that could not be done, and so others pursued the subunit vaccine sort of path. What really inspired you to decide, to pursue this difficult route of, manufacturing irradiated sporozoite? What made you think this would be the most sort of ideal way to develop a more effective vaccine? Can you just briefly share with us the experiences, the challenges, and how did you overcome them? And what do you think, in your view, was the breakthrough discovery that you think made it possible for you to pursue the PFSPZ vaccine?
Sure, we have enough time. All right. So let me just say, let's go back and give credit where credit is due. I mean, there have been studies done even in India in the 1940s with chicken malaria that showed that you could actually protect with sporozoites. And then in 1967, Dr. Snusiswag and team um, blanking out on names here, but I'll give you, come back to me later, showed in mice that you could get partial protection by immunizing mice with.
Was this the group from Florida?
No, this is from NYU.
Oh.
Okay, that you could get partial protection against plasmodium by immunizing with radiation attenuated Plasmodium berghei sporozoites. And then amazingly, that was published in Nature in 1967. And in 1973 and 74, two different groups, one at the University of Maryland, led by David Clyde, working with the team at NYU, published on that if you protected people, this was in December of 1973, by the bite of mosquitoes that had been irradiated, by the bite of these mosquitoes, inoculating sporozoites, so radiation attenuated sporozoites, you could get protection. And then Dr. Riekman, working in Chicago at Rush Medical Center with Dr. Bodwin at the Naval Medical Research Institute, a few months later published similarly these types of results. And so now we are in 1973, 74, and showing that we actually can protect people against malaria. And then I would add that in 1978, Dr. Bodwin did the first study on what I'll tell you about is CVAC, and showed that if you gave live sporozoites with anti-malarial drug, you could also get very good protection. So we're in the 1970s. We know that you can actually protect against pre-orthocytic stages of malaria, that nobody could even conceive of how you would actually make a vaccine, which has to be aseptic and purified in mosquitoes. So the work set out to try to understand the mechanism of protection and then identify the target of protection and make a vaccine that duplicated that. And I told you already about the monoclonal antibodies, the repeat region of the CS protein. And then what was really amazing was that in August of 1984, the team from NIH, led by Dr. McCutcheon and Dr. Miller, using a monoclonal antibody from Walter Reed, published the sequence of the circumsporozoite protein. Not the sequence of the genome, but just the one protein, all right? And in Science, that was in August of 1984. There was a big announcement, we're gonna have a malaria vaccine in a couple of years. But in June of 1987, we published the first paper on the first clinical trial of that, Rip Ballou being the first author, I was the second, in which we immunized and did a one-year study. So from August of 1984 to June of 1987, which is less than 3 years, we went from identification of the gene sequence to the first malaria vaccine trial of PFS CSP recombinant protein with adjuvant, which is the predecessor of RTSS. We often talk about translational medicine now. I defy anybody, but we did it faster with COVID-19, right? With SARS-CoV-2, the international community did it faster than that. But with investing about $100 billion in it, right? And again, I would just put in as an aside that we're investing $3 to $4 billion a year in malaria, and we've invested perhaps trillions in COVID-19, in terms of it, and appropriately so, and it's a worldwide pandemic. But it takes money to do these things properly and to do them quickly. Any case, we have the irradiated sporozoites going down one path, and then we start doing studies which showed that, in fact, the protective immunity was not due to antibodies induced by irradiated sporozoites, first done in mice. It was due to cellular immune responses, particularly CD8 T cells that targeted the infected liver cell. We now call them tissue-resident T cells. And there was a series of studies that came out from our laboratory, NYU, NIH in the late 1980s, which really targeted in on this and showed that if you took fully immunized mice, you depleted them of CD8 T cells, they lost their protective immunity. And then we were able to isolate those CD8 T cells against the CS protein and show that they eliminated infected hepatocytes from culture. So by 1989, 1990, I knew in my heart of hearts that the approach that was being taken with RTSS, which was then just being made with the CS protein approach, whilst it could be important, and we've seen that it can be, and protective, it was being handled, and we had already studied 5 different forms of CS protein, many different adjuvants, all of which are really the same adjuvants we're studying today. And we decided in my team at the Navy to go a different route. And the route was to go back and start immunizing people with radiation attenuated sporozoites by mosquito bite, not to make a vaccine, but rather to understand just what Ali asked earlier, the targets of protective immunity, the mechanisms of protective immunity, and then to build a subunit vaccine that incorporated the identified targets that induced the protective immune responses. And right as we were starting that, the first indication that DNA vaccines could actually work came out. And we went forward and we started to use DNA vaccines because we did all kinds of studies. We immunized people for 10 years with radiation attenuated sporozoites. And then fast forward to 2002, I had retired from the Navy. I was leading the biologics effort at Sanaria Genomics on the human genome, human immunotherapeutics, and so on. It was kind of like a fish out of water. And many of you will be familiar with something called the Keystone Symposium meetings. And we had a meeting that I was organized, was the co-organizer of with Carol Long. And at that meeting, I had a session which was entitled Malaria Vaccines, Why is it taking so long, right? And then I asked at that meeting, everybody, when they thought we would have the first licensed malaria vaccine. And the team from RTSS, from GSK said in 2010 or 2011. And everybody else seemed to think it was going to take till like 2025. And at that particular point, I was at a place that had sequenced the human genome. Previously, it had been stated that it was going to take 10 years and $3 billion to sequence the human genome. But we had done it at Sanaria Genomics after the announcement of Craig Venter at 1/10 the cost and in 3 years. And so I thought, we have a vaccine in front of us. It actually works. Why can't we make it? So I resigned from Sanaria Genomics, started this company in the breakfast room of my house with my son, who you saw on the motorcycle earlier, who was getting ready to go to law school and is now our chief legal officer. Unfortunately, my wife had a job at the time as the vice president of another biotech company, with the idea that if we could do this for the human genome, why can't we do it for mosquito production of sporozoites? So that's how it started.
So in the beginning, when you let's move this from that step. So in the beginning, when you started this, you were injecting people using mosquitoes. So you had the sporozoites in the mosquitoes. You were feeding mosquitoes into that, and then you transitioned to IV injections. Can you discuss that process?
Sure.
Those changes and what the lessons were?
So we knew from animal studies that the most effective way to immunize was by IV injection. This is the paper on the left here, in which I summarized all of the data on irradiated sporozoites, and that was the foundation for starting the company. But you can see, even in that paper, we never mentioned making a vaccine for irradiated sporozoites. It was still kind of like too much to think about. We then started the company, spent the next 7 years developing how are you going to make aseptic mosquitoes, aseptic sporozoites, purify them, cryopreserve them, and so on and so forth. And we did have excellent funding through Path MBI by the Gates Foundation, about $30 million. And the team led by Judy Epstein wanted to do a study by giving it IV, because all the data suggested that was the way to go. But everybody wanted to see if we could do it more practically first. So we're against our better judgment. We went forward by sub-Q and ID. And the first paper, which was published in 2011, we got no significant protection, but we also got it published in Science because we showed why we didn't get protection, and then we showed that if we gave the highest dose we gave to humans to monkeys, compare those that got it sub-Q or those who got it IV, and we looked in the liver for tissue-resident CD8 T cells producing interferon gamma that were specific for sporozoites. We got none when we gave it sub-Q, but we got 3% of all the CD8 T cells in the liver were specific for sporozoites. And that was done with Bob Cedar, who's now the first author on this next paper. And with that data in hand, and I would mention that with the original, with all that information and the data that we generated, we no longer got any funding from the Gates Foundation, but we were able to go in and talk to Tony Fauci, who's been quite prominent in the last year, and he gave us the funding to go forward with another trial, which is we gave it IV. And again, we showed dose-dependent protection. In the first two groups, we got no protection, the lower doses. And I thought that I really was going to have to retire at that point. It was the end of it. Might as well go back to something else. But in the last group, we got 100% protection against homologous, meaning the same parasites in the vaccine and the challenge at 3 weeks after the last dose of vaccine. And that's what this paper is about.
So at that point, you've already started the company. You're manufacturing now, but still really dissecting by hand. Can you talk about how you do this manufacturing right now?
So these are earlier pictures. At this point, if you see anybody dissecting or anybody manufacturing, they look like all the pictures you've seen of SARS-CoV-2 with head to toe, not a millimeter of skin exposed. And so we had to develop all of these methods and when we started, most people in the malaria field could dissect maybe 30 to 60 mosquitoes per hour, and our team of dissectors can now do 300 to 500 mosquitoes per hour. And so that's where we are right now, but we've been working with the Johns Hopkins School of Engineering and Robotics, and we'll soon be able, we believe, to launch a robot that can actually extract the sporozoites from the mosquitoes. But in the meantime, yeah.
So you culture the sporozoites in the mosquito, and then the mosquitoes are dissected, and that's how you produce the sporozoites aseptically.
Right.
Okay.
But one of the things where we're moving, we hope, and we soon should have a paper coming out on this, is that led by Abraham Eapen in our lab, we've developed a method for producing sporozoites without mosquitoes in bioreactors.
Wow.
So that's the goal, would be that to transition with the mosquitoes to partial robotics or complete robotics, but to eventually eliminate the mosquitoes so that you could make this in a culture lab just like any other culture.
Without losing the variability?
Yeah.
Without losing
the antigenic variability on the surface?
Well, no, you would get the same things we get right now, the exact same format, but it'd be much more efficient. We've already shown that when you do the transition from gametocytes to oocysts is about 30 times more efficient in vitro than it is in mosquitoes.
Excellent.
So,
go ahead.
So this would dramatically reduce the cost of goods.
Thank you, Steve. Steve, I wanted to maybe go to some of the very commonly cited concerns. I think some of them we have addressed already by this new technology moving away from the mosquitoes. So perhaps addressing the challenge of manufacturing the vaccine in large quantities. But there are other issues which maybe are coming up. One has to do with the fact that this vaccine needs to be given intravenously. So for someone working in a malaria control program, he might have an issue and say, this is almost impossible to administer in peripheral healthcare facilities, given the lack of trained healthcare workers with phlebotomy skills. And also it has to be stored in very cold temperatures. How can you address some of these concerns as far as PFSPZ vaccine is concerned moving forward?
So, as I said earlier, the ideal vaccine would be a single dose that lasts for your whole life that you can rub on your skin, right? I mean, or you could drink. Something very, very simple. But at the other extreme is that you want a vaccine that has the highest level of protective efficacy and that is extremely safe. So we know that our vaccines are incredibly safe and well tolerated. In 13 double-blind placebo-controlled trials in Africa, administered by direct venous inoculation, there's been no difference in adverse events between vaccinees and controls. So we have a highly well-tolerated vaccine that's extremely safe, and we're shooting for a highly protective vaccine. So now let's talk about the downside. Forget about the manufacturing, that's our responsibility. But when we launch this vaccine, we're asking people to take a 25 gauge needle and inject, probably it'll be about 0.3 mLs. We've been in the past projecting 0.5. When we started, everybody said that this is impossible, it can't be done. But we've now done it down to 1,000 injections in infants in Kenya. The team from Kenya has published on this about the ease, the tolerability, and there's no question it takes more training. And all the data that we've generated so far indicates that whether you give it to an adult or a 2-year-old, there's no difference, and it's extremely easy. Ali, you know, because you've given it. And so it's not the same. It will be a balance in terms of administration. If it's as good as we project it to be, if it does the job that it needs to do, is it going to be worth it to train the people to do it? And then please remember again what I've told you before about there's different constituent populations for this. We are not envisioning giving this the way that, at least in the first few years, the way that other vaccines are given in the expanded program for immunization in infants or very young children. We're envisioning it on a campaign basis, whether that's for elimination programs, seasonal vaccination in the Sahel of Africa, giving it to travelers. So we believe that in those settings, it would be very easy to train people to do this. And it's no different than drawing blood, which is done in all those different settings, except that it's a smaller needle in general. So it is an issue, but so far we've done this in 7 different countries in Africa in a total of about 3,000 people, and it hasn't really proved to be much of a problem. And I would ask you to comment on that, Ali, from your perspective, because you actually have given it.
No, I think, yeah, absolutely, Stephen, as you've said already, that we have done it with the same type of healthcare workers that you find in these rural sites in Africa. So I think it's, as you rightly put it, it's a matter of if you have a good vaccine, which is very safe, then definitely that is gives us impetus to then go that extra mile to train people, because you are then going to reap the benefit of protecting your population. So it's that, what you need to do to sort of reap the benefit of a good vaccine, vis-a-vis if you don't have a good vaccine that is, effective, efficacious, and also safe. So I have done it. It was very easy to train, I think, and it only takes a couple of practical sort of, to be able to master it. And I think it is possible to train people to do it.
Yeah. So I would just say that I don't think anybody who's actually done it has any problem with it. We hear problems from people who haven't done it. And I actually think, I don't want to be so negative, but I think it's an insult to the healthcare workers in Africa that say that we couldn't train them to do this very effectively. So that's one thing, the DVI. The second you brought up is the liquid nitrogen vapor phase. So we have to be very clear. As I said before, these are eukaryotic cells. They can only be stabilized in vapor phase liquid nitrogen at minus 150 degrees centigrade. And that has advantages and disadvantages. There's 11 different vaccines in sub-Saharan Africa, veterinary vaccines that are distributed in liquid nitrogen. The all artificial insemination of 600 million cattle, even in Africa, is done in liquid nitrogen. It's available everywhere. And we don't have time to go into great lengths about that. We've published papers on modeling the introduction of a vaccine in vapor phase liquid nitrogen. And I only just leave you with two thoughts. Number one is, if I make a vaccine in the United States and ship it to Nairobi, and it has to be at 4 degrees centigrade, and it's a new vaccine, you need to build a new facility with new refrigerators, with staff to maintain those, with electricity backup for those refrigerators and so on. And if I have it in vapor phase liquid nitrogen, I send you a tank, you can have an empty warehouse and just put it in there, and all you have to do is recharge that tank. The electricity requirement that this bypasses is huge. And we can talk about that at much greater length in the future. But that's it. We actually think that there's a huge advantage. The Ebola vaccine went to Africa in dry ice and minus 80-degree freezers, much worse than this. And the initial Pfizer vaccine was going out in ultra-low freezers and dry ice. If they had our vials, they could have sent it in vapor phase liquid nitrogen with no problem in tanks that can last for months. So yes, we've had to blaze a new path. It's not the path that people are used to being on. And it'll be our job to demonstrate, which I think we've done quite effectively so far, that we get to the point of having a product that it's really not a problem.
And I mean, Steve, we've got to move this forward, but and I believe you guys have borrowed from this as well. The veterinary side of things already do a lot of liquid nitrogen work in rural Africa with cattle. So,
yeah, well, in Tanzania, for example, the veterinary industry, we've met with the minister involved with that, and there's 4 plants for producing liquid nitrogen in Tanzania in 4 different parts of the country to support the veterinary vaccine effort, right? I mean,
yeah. So I think that's Sheila, please.
Yeah, thank you, Fred. Steve, could you please share the status, any status updates on the vaccine trials that you're currently conducting at Sanaria?
Sure. So because we have this new type of product, and there's really no basis for how you determine how you give whole eukaryotic cell vaccine. Forget about just sporozoites. It's any whole parasite or eukaryotic cell vaccine. We've had to do empirical studies to figure out the best route, the best dosage regimen. We've done, just for the radiation attenuated sporozoite, 20 different trials in multiple countries in Africa, multiple countries in Europe, multiple sites in the United States. I know that time is limited here. We have a publication coming out from the team from Mali, from the Malaria Research and Training Center, and the Laboratory of Malaria Immunology and Vaccinology from NIH in Lancet Infectious Diseases, showing that with a 3-dose regimen, we can get about 52% protection in adults over the course of seasonal transmission in the Sahel and Mali. A similar study showing protection lasts for 18 months in Burkina Faso. So we've been focusing a lot initially on adults, and we're starting children's studies. But what I'd like to talk about a little bit, as I know we're getting towards the end of this, and I can talk in great depth about most of these other trials, but PFS-PZ vaccine, the radiation attenuated sporozoite vaccine, is moving forward towards final phase 2 trials and then phase 3 trials next year. We're going on 2 different pathways. One is a vaccine for travelers, and the other is which we intend to get licensed in Europe and the United States. And the other is a vaccine, of course, for populations in Africa. We're focusing initially on 2 to 50-year-olds. We have data from infants in Kenya that the radiation attenuated sporozoite vaccine does not make the T-cell responses that we need in infants. We have to go to a little bit older children to get those responses. With the current regimens, we're working on adjuvants and ways to get around that. So we're focusing in Africa on 2 to 50-year-olds with tremendous support in Equatorial Guinea, but tremendous support also in Mali. So we're going forward with those studies. What will be appearing in Nature in a few weeks is a paper that we did with the team with the Patrick Duffy's team from the Laboratory of Malaria Immunology and Vaccinology on CVAC. So CVAC is the chemo-attenuated sporozoite vaccine. I wonder, Fredros, if we could go to the...
that was going to be our next question. So
yeah,
talk about CVAC. Go ahead, please.
Yeah, so could we go to the sinusoid of the liver? I think I could explain that best from there first.
Go back.
Yeah, right here. So if you look at this, this is a snapshot of the sinusoids in our liver. And what you see in purple there is the blood in the sinusoid. And then in gray are the hepatocytes. And lining the hepatocytes are endothelial cells and Kupffer cells. And the green squiggles are sporozoites. And now below you see different bars. And what we see with the first bar is PFS-PZ vaccine, and then our first generation genetically attenuated sporozoites. And what happens is the sporozoites go into liver cells, partially develop, round up, and then they stop. They're metabolically active and non-replicating. They express about 1,000 proteins. If you go to the other extreme, which is the bottom one, which says PFS-PZ, CVAC, chloroquine, the sporozoites go into the liver cells. They replicate about 50,000 times in the make 50,000 more parasites. They express about 3,000 proteins that weren't expressed in the early liver stage, meaning the immune system is given many more targets for making protective immunity. They rupture into the bloodstream where they're met by chloroquine and killed before they can replicate. The advantage of the irradiated sporozoites is that they're never developed to the blood stage, and we've given billions of sporozoites without breakthroughs, and they can't cause clinical malaria. The disadvantage of the CVAC chloroquine is that they can get out into the bloodstream, and they can cause, particularly after the first dose, some symptoms. And if somehow we didn't give the chloroquine properly, we could get malaria in these subjects. So that's a concern. But what we've shown is that for the same dose, if we can get better protection with CVAC chloroquine at 1/10 of the dose than we get with PFS-PZ vaccine. And there's a study that Ali did in Equatorial Guinea, which was recently published, in which we showed that if you gave a dose of 100,000 sporozoites of CVAC, we got at 16 weeks, 50% protection against challenge. And if you gave 2.7 million sporozoites, irradiated sporozoites of the PFS-PZ vaccine, we got no significant protection. So
is that this? Wondering if we have. This is.
No, it's not that. That's a different study.
Different. It's a different study. Right? Okay.
It's this paper here in American Journal, right?
This is from Saidi, from Jongo.
That's from Jongo and Ali, and that was done in following Ali's first study in Equatorial Guinea. But if you go back to the liver cartoon,
to the sinusoid, brilliant, yeah.
Yeah, go back. All right, one more, good. So now what we've been doing and what I'm going to tell you about now is with the team we've done this in Mali now, and we've done it in the United States. If we give pyrimethamine, we stop the parasites about halfway through the life cycle, in which case they can't get in the bloodstream, which means they can't cause malaria symptoms and they can't cause disease. But if you took the drug wrong, you still could get disease. So now working with Stefan Kappa's group and a group in Leiden, Chris Jance's group has also done this. We've knocked out a gene called MAY2, which allows the parasites, this is now genetically altered, we call it LARC1, late arresting replication competent parasite 1, that goes all the way to the late liver stage, and then it stops. So we can get the advantage of having 50,000 more parasites, 3,000 more proteins, without the disadvantage of going all the way to the bloodstream and actually potentially causing illness. So where we're going now, and now I'm going to tell you about the 3 stages of this, is we had chloroquine, which is the best so far. Pyrimethamine works, but now we're going to be moving towards this as the perhaps not ultimate, but some, penultimate vaccine. So now we can go. This is really not CVAC. This is now late genetically attenuated.
Brilliant.
It's a genetically attenuated CVAC, right? So it gets all the advantages. So this is a paper done by the team in Germany that was published a few weeks ago in Nature Communications, in which they used 110,000 sporozoites. Our dose for radiation attenuated sporozoites is 900,000. So we're talking about an eighth of the dose. They immunized on days 1, 6, and 29. So it means the immunization is over in 4 weeks. And they challenged at 12 weeks with parasites that are heterologous. They're more different from the parasites in the vaccine than over 700 isolates of Plasmodium falciparum that were identified by Joanna Carr and Silva sequence. So very heterologous. And what they got with this dose was 77% protection, sterile protection at 12 weeks, 3 months after the last dose of vaccine with this approach. Now, what is not shown here, which is going to be coming out soon, and this is with chloroquine, is that when the dose was raised to 200,000 sporozoites by Pat Duffy's group, and then challenged the same way, we got 100% protection against these very heterologous parasites, again, with a dose that's about a fifth of the dose of irradiated sporozoites. So we are able to now achieve 100% sterile protective immunity against a parasite that is more distant from the parasites in the vaccine than any parasite in Africa with this approach. Now, also in that paper,
So that, sorry to interrupt you. So I believe we have, can you explain? So is this the same type of attenuation
yes,
as the
these
other
are
one?
all the same. It's all the same approach. CVAC,
Exactly.
this is CVAC chloroquine. John Go's paper is CVAC chloroquine. He used 100,000 sporozoites. We've now moved it up to 200,000, and we're getting this phenomenal protection.
So just one step at a time. So 100% protection.
Yes.
Attenuation is done by chloroquine.
Right.
And this works at high doses.
It's not very high. It's much lower dose than is irradiated sporozoites. It's
so
about a fifth to a tenth.
In the work by Saidi Jongo, my colleague, and Ali here, it appears, and I don't know if we have that slide at some point, I think Sheila was going to discuss this with you, that at a certain, if you increase the dose too much, then you lose that protection, right?
That was with irradiated sporozoites, not with CVAC. We don't know that with CVAC yet.
Okay. Sheila, did you want us to go to that so that we just finish that discussion actually?
Okay.
Yeah, sure, Fred.
Yeah. Go ahead, Sheila.
Okay.
Yeah, so the question there is whether the dose really matters, and I guess you've answered that. Yeah. Would you like to probably expound?
Sure. So we also have a study in which the same dose that gave us 100% protection in the United States was used in Mali. There's another twist. Let me just tell you that immunizing with a whole parasite is actually quite complex. And there's many, many studies that show that immunity is suppressed if you have concomitant Plasmodium falciparum infection at the same time. And that was a problem in this study that we just showed with Django, is that actually we didn't clear the parasitemia. We've shown now in 5 different studies in Africa that if we don't give individuals anti-malarial treatment before their first dose of vaccine, that we don't get protection. We've done that in 5 studies and got protection in all 5. In 3 studies, we didn't do it. We didn't get protection. So, we've had to increase the dose in Africa for CVAC. We have the first study coming out where I believe we now have protection for 2 years in Africa with CVAC pyrimethamine. We haven't done the chloroquine yet. So, but you do need a higher dose because the immune responses that we're seeing in African adults are lower than what we see much lower than what we see in European or American adults.
Steve, if I may interject there, can you also maybe also explain a bit, because why do you think this is the case? Why are we seeing lower immune responses in semi-immune adults as compared to what we've seen in malaria naive adults? Could you expand a bit on this? And
sure. So I think that there's a major explanation and a minor explanation. The minor explanation is that because of pre-existing immunity, some of the sporozoites that we inject are getting wiped out by the host immunity before they can do what they have to do. I think that's the minor. The major is something we call immune dysregulation, which has been well described. And it's actually been shown for 30 or 40 years that malaria itself is immunosuppressive, and that even to other vaccines, not just our vaccine. And as such, it's almost like people, as I said earlier, were desensitized to the malaria parasite in the same way as an allergist would desensitize you to a bee sting. You get over and over and over again very small doses, meaning one infected mosquito every 4 days or whatever, you become desensitized to it, and you can't mount an immune response to it. And that's the basis of desensitizing for allergies. I think it's something like that. It's more complex than that. There's a huge literature now on that. And the question is, can we overcome that? What we've been able to do now in five different studies in Africa is get to as high as 57% protection in adults. The data show that children have much higher immune responses, and that our expectation is that in the study that we're now starting in Mali, we will end up with much higher protection. But the adults, so far, we haven't been able to get beyond that 50 to 60% protection. We have an adjuvant that we were working on that we think may help with that. But it is a problem for adults. And as I said, at least in one study of RTSS AS01 that was done in adults in Western Kenya, there wasn't significant protection.
Cool. So time is not on our side, but
thank you, Steve. Could you also comment on route?
Sorry, Sheila.
Sorry, Fred.
Go ahead, Sheila.
I would like Steve to comment very briefly on the route of administration. Should this be tablets taken orally?
Yeah, so I think that we discussed it, and Ali discussed it, and there's quite a few publications, particularly from Kenya, on the practicality and the acceptability of the route of administration. The bottom line, in my mind, my point is that we know that it's different. However, everybody who's worked with it doesn't think it's really a problem. Those people who haven't worked with it really think it's a problem. I could go on and on about what people told us about how difficult this was going to be and how we were going to even kill people by doing this, even in the United States. And it hasn't been a problem anywhere. If the vaccine is good enough, we believe that it won't be a problem. And I actually think, I hate to be so specific, but I think it's an insult to healthcare workers the world over to say that if this can't be done. I know they can do it.
Thanks. So I just for some clarification here, I just want to clarify that just to close that chapter, there was still sterile protection in the work you guys did with Dr. Jongo with some of the doses. So just to keep that rested. We're going to skip some of this, but you mentioned the issue of adjuvants, and here is an old paper of yours, Steve, working with some lipids.
Right.
In the study of the sporozoite vaccine, you don't hear so much about adjuvants as much as you hear it with the RTSS. So can you talk slightly
Sure,
about
just very briefly, there are no adjuvants for live attenuated vaccines. The concern is that if you mix it up with an adjuvant, that you'll glump it up and the live attenuated vaccine will no longer be alive, right? However, we have an adjuvant, which is a glycolipid that we can mix with the sporozoites that doesn't kill the sporozoites. And in mice, we've been able to show that we can go from a 3-dose regimen to a 1-dose regimen. We've studied it in monkeys, and we're studying it further right now. And we've made it. It's taken some time to make it under what we call GMPs, good manufacturing practices. And so we're looking forward in the next few years to determining whether addition of this adjuvant can help with improving the protective efficacy in adults in Africa, and B, improve the T-cell responses and the efficacy in infants in Africa. Both of groups. We're very happy. We've gotten the only consistent protection in adults in Africa of any malaria vaccine. We've done it now 5 different times, but it's still not as good as we would like it to be. So the adjuvant may help with that.
Thank you. Only 3 questions from my end. I believe there's a few from Ali and a few from Shayla as well, but very quickly, Steve, let me just check could you comment a little bit on how this concept of CHMIs, we should have covered this earlier in the introductions, but we didn't. But could you describe a little bit how this concept of controlled human malaria infections have revolutionized and enabled the vaccine trial processes that you're doing, that you couldn't do before?
There have been controlled human malaria infections since the 1920s, when actually controlled human malaria infection won the Nobel Prize for treating neurosyphilis. And then there were a lot of studies to develop malaria drugs through the 1930s, 40s, 50s, 60s. But with the advent of the continuous culture of Plasmodium falciparum in 1976 by Traeger and Jensen, and then different other developments, Jerry Vandenberg at NYU, who also was instrumental in all of the early work with Ruth Nussensweig, showed that he could produce gametocytes that were infected to mosquitoes in 1981, and then Kent Campbell and the team at CDC showed in 82 that they could actually get those to produce sporozoites. We in 1986 did a study in which we used mosquitoes infected. It was led by Jeff Choulet, who you saw injecting me earlier, that we could actually infect volunteers. And the whole idea was to be able to study the vaccine, the first CSP vaccines, by controlled human malaria infection. And I really believe that the foundation for everything we've done has come from the controlled human malaria infections. And of course, the knowledge that irradiated sporozoite vaccines worked in humans came from controlled human malaria infections. We can rapidly determine if an antigen is important or not, or if an approach like what we're doing is not. is, we go to LARC1, we'll be able to transition very quickly. We do a controlled human malaria infection, and then we're out to the field overnight.
Would this enable you to?
But let me just finish just for a
2B?
second, Frederick. So that's controlled human malaria infection. But now you see this paper by Safe Shekalagi,
Yes.
which was the first controlled human malaria infection in Africa.
Right.
And what this has done is that this has now been done in Tanzania, Kenya, Mali, Gabon, the Gambia, and Equatorial Guinea. And this has enabled researchers all over Africa, and it's actually been done in countries in Europe also that have never done it before, by our injection of sporozoites, to actually study malaria in a way that they never would be able to study, before. So I think it's been an enabling technology, particularly in Africa, for studying malaria, but also in the whole rest of the world.
Sorry about that. Go ahead.
Yes. So, and now, as I think is outlined in this paper, initially it was only used to study pre-erythrocytic stages, and now it's being even studied to study transmission blocking vaccines, sexual and mosquito stage vaccines.
Thank you. Thank you very much. And congratulations also to my colleagues, Ali, Dr. Chef Sekilage, Asaidi Jongo, and also our colleagues in Kenya, actually, who have published at the same time in the same year, the CHMI.
Yes,
work.
in Nairobi. So we did it
Yes.
first in Nairobi, and now it's been done in Kilifi and Kisumu.
Right. So we're going to skip that. Sheila, please.
Yeah, thank you, Fred. I think one more question that we were discussing with Fred earlier on was about the PFSPZ consortium. So what are the achievements so far, Steve?
So this is one of the endeavors that I'm most proud of. All right. Over the years, we have been, we all, we're scientists, we're physicians, we're physician scientists, we're public health individuals. And, malaria's problem, it's all over the world, but the major problem is in Africa, in sub-Saharan Africa. And there's been lots of discussions about north-south, south-south, all kinds of interactions. But I feel like the International PFSPZ Consortium has really been one of the ultimate success stories in regard to having this kind of collaboration. So that what you see here is the snapshot of the most recent meeting, which was in December or late November of 2020, in which we had 231 attendees from 68 institutions in 27 countries. And they come forward to share in real time their results, whether it's in the lab or it's in clinical trials, without having to wait for publications. Nobody says, we got to wait till it's published in the New England Journal or wherever it might be, so that we can do what we call adaptive clinical trial design, and people can share to make their trials better. And you see, individuals from so many different organizations, so many different countries, and we're the way this has gone. It started out as a 7 a.m. meeting on diagnosis and controlled human malaria infection at the American Society of Tropical Medicine meeting, and has grown into until COVID, twice a year meeting with hundreds of people from hundreds of organizations. And I think I like to think that it's a model for how we can really pursue global health research together as one team dedicated to solving enormously difficult and important problems.
Thank you so much, Steve, and congratulations. At Ifakara Health Institute, we are most proud to be part of the consortium. And I just wonder if Ali, not as a co-host now, but as a scientist in this consortium, you have any specific comments about this consortium? So.
No, that's just to echo what Stephen has just already said. I think it is, always great strides in science are made through collaborative efforts. And I think this is one example. And as you said, it's quite unique. People coming together and share. And again, unlike other, I would say, Stephen, is, these people are willing to even look for funding elsewhere themselves and, and contribute to the consortium sort of collective sort of knowledge generation. So you have people from various areas applying to different funding and with common goal. So I think it's quite an achievement. I would also like to congratulate and also say that we are definitely glad to be part of this consortium.
Thank you so much. So we have a hard stop. This very quickly from you, Steve. It's difficult to close a meeting on malaria vaccines without referencing this recent study. You mentioned it a little earlier. This is the R21 study from Burkina Faso. Any 1 second sentence on this?
So I think these are very exciting, encouraging results. We have another CSP vaccine, which has given good protection. I would mention very clearly that it's been stated in a lot of articles it was for a year, but it's really 6 months because there was only one case of malaria in the control group during the second 6 months. These are, exciting. We've seen from what you showed from RTSS that different areas, different epidemiologies, we may see different types of results, but this is an exciting, encouraging, not necessarily unexpected. And question really is it any different from RTSS? It's more or less the same vaccine. There's a few more elements in it. It's a different adjuvant. And we'll just have to see as we go forward. But it's good to have positive data.
Thank you so much. Thank you so much, Steve. It's been incredible listening to you. You noticed that we have a lot of questions. We didn't cover everything. We have a hard stop today, unfortunately. There was a question on the chat about comments on the Pararoya vaccine from our colleagues in South America. We will follow up with you on this by email, and we will send you also the entire chat script for this. Anybody who wants any information regarding this, please get in touch with us. Otherwise, Steve, any last words from your end on the session today? And then we can get our colleague Ali and Shayla to close.
Okay, well, first of all, I want to thank you and Ali and Sheila and everybody else who's been instrumental in organizing this. I think I'm very proud and honored to have been invited to interact with you. I wish I could see all the people who are online, at the same time. But I think you've done an incredible job in putting this together. You've done it. This is the best format I've ever participated in our Zoom era, COVID, pandemic era. We've really done this. The technology part of it has been done perfectly. And I would just like to comment just at the end that we have to heed the words of in our annual World WHO Malaria Report, the words of Dr. Alonso, the Director General of the Global Malaria Program. So we need, and it was there on the International Consortium site, when he addressed that team, we need new tools, and vaccines are the most effective tools for limiting any infectious disease. It doesn't obviate the need for other tools, with nothing against them, but it's taken a long time and an incredible amount of work, and we have many ups and downs in this process. And it's not for the faint of heart, but the prize, the goal, and it's not a winner take all. It's not like if we have RTSS implemented, that's the end of the day, or R21, or our vaccines. It's too hard a problem, and we need everybody's efforts as we go forward. And that's why I invite everyone to take part in the International PFS-PZ Consortium. It's really incredible. We don't pay. Everybody comes, and when we have in-person meetings on their own, funding, somehow they manage to do it. They raise money for their their own trials and we conduct together. It's really, I think, the best example. And we have many other examples. The collaboration between the Ifakara Health Institute and the Ministry of Health and
Hey, how are you?
Yeah.
Yes.
So I want to thank you. I hope that it's given people the impotence, the initiative to really go forward themselves and really risk some things. And you have to risk if you're going to make it in this field. And you have to be able to pick yourself up and dust yourself off, because you're going to get knocked down over and over again by malaria. It is a tough foe, but we're making progress, inching forward every day, and we have to keep up the work. So thank you.
As you can see, there was a lot of interest. There was 220 people, 215 people at the peak, and many of these are actually sharing computers. So there are many institutions where people have a shared conference hall listening to this, to the masterclass. So there's probably 100 people participating. We've been screening live on our YouTube as well. Very, very much engaging. Thank you so much. So Shayla and Ali, please.
And I'll be able to get a copy of the chats, right? I mean, I didn't look at them. I was talking too much to pay attention to what the questions that were being asked. I was relying on you. But
No problem.
I really thank everybody for spending this amount of time listening to me talk.
No worries. Ali, please, and Shayla, please go ahead.
Yeah, thank you so much. Thank you so much, Stephen, for gracing our masterclass today. We really enjoyed it. It was quite informative. And I'm sure most of us who didn't know much about vaccines, we now know a lot more than we did before. So thank you very much for spending the whole 2 hours with us. Ali?
Thank you, Shayla. Thank you very much also, Fedros and Shayla, for inviting me today to co-host this. I've been participating, of course, as a participant in other master classes. Thank you very much, Stephen, for agreeing to participate and share with us incredible story and information. And as an African scientist, I'm really proud to be part of this effort to look for a malaria vaccine and participating in this process as well. And again, I take the words from Stephen that you have to risk, you have to push forward. And to the young scientists, I think this is a great lesson and message to take home. Thank you very much.
Can I just say one last thing before we leave? In a session like this, you can't even begin to give credit to all of the people who have made contributions. And I apologize if I've missed somebody along the way. And I know that I've missed recognizing the efforts of lots of people. And I apologize for that. But there's only so much you can say.
And we can always have another session, but mostly really, Steve, just to say thank you so much, and thanks to my colleagues. Apologies to all the participants again. Today we had a rush because we have a hard stop right now, but until next time, we look forward to having you again in our master classes. The 26th edition is coming next week, but this was great, super. Thank you so much, and thanks everybody. Have a good day.
All right, bye-bye.
Bye.
Bye-bye.
Bye.